this time. Okay.
Why does it have to get us?
Huh?
Why does it have to get us?
Hey, don't you want the camera facing you?
Why should it face me?
So you can write stuff on the white.
Oh, that is right, it's actually.
Yeah,
Not bad, not bad.
I thought.
I see, because can you see the whiteboard? Oh, yeah, perfect.
Plus, they get to see your smile from face up.
Yeah.
Oh, hush. Oh, okay. So, I know we wrote these numbers earlier, but let's rewrite them again, because I wanted color. Me and Rhea have color. So Fibonacci sequence is a sequence defined by the recurrence relation. The current term, f sub n plus 1, is equal to the previous two terms, f sub n plus f sub n minus 1. So 0 and 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. So we can get these numbers that we got yesterday. 3 plus 5 is 8, 13. 13 plus 13 is 21, 13 plus 21 is 34, 21 plus 34 is 55. 34 plus 5 is 89, and 55 plus 89 is 144. And so there's lots of myriad facts that are pretty groovy. If we went down the road and saw F615, we would see that that's 610. There's something to notice about these columns. And that one, well, it doesn't fit on the page. But what we notice about those is that they're all divisible by 5. Yeah. And also look at the subscript. The subscript here is 5. The subscript here is 10. The subscript here is 15. Those three numbers are divisible by 5. Technically, the number 0 is divisible by every single number in the world, including the number 5. So every fifth number, if I jump 5, jump 5, jump 5, get to that one, we get a number, a Fibonacci number that's divisible by 5. But what's unique about this is some of them end in 0 and some of them end in 5. And so the ones that end in 0 have a subscript, like F30 ends in 0. F45 ends in 0. F15 ends in 0. So what is the connection between those subscripts? F15, F30, F45. Every 15th Fibonacci number is divisible by 10. And every fifth Fibonacci number is divisible by 5. So that's kind of a groovy thing. That's like one of quirky properties. I also spoke yesterday how, oh, maybe I didn't. Did I speak about 144 and 8 are special? Yes, I did. Alexis, you said that? Yes. They are the only numbers, Fibonacci numbers, that are the form a to the b. Where a is, well, not, there's silly things, like you could have 1 to the 1. I'm not talking about that. We're talking about an integer a that's bigger than 1, and an exponent b that's also bigger than 1, because the number 13 is 13 to the 1. But we're talking about cool things like 8 being 2 to the third power, 144 being 12 to the second power. Right? So it is known that those are the only two numbers, which is kind of miraculous, that are perfect powers. These are called perfect powers. So let's look at another sequence that's very much like the Fibonacci sequence. Why? Because it has the exact same recurrence relation. Add the two previous terms to get the next one. So here we added the two previous terms to get the next one. But the only difference is that this one's the Lucas Fibonacci started at 0. The Lucas sequence starts at 2. So you wouldn't think much of a difference would be had, but you're gonna see it's wicked different. By the way, we pronounce this Lucas, not Lucas. That's an Americanization of the beautiful French name Lucas. So we have start with a 2, and then we have a 1. Let me get my cheat sheet. 2 plus 1 is 3, 1 plus 3 is 4, 3 plus 4 is 7, 4 plus 7 is 11, 7 plus 11 is 18, 11 plus 18 is 29, 18 plus 29 is 47, 29 plus 47 is 76, 47 plus 76 is 1, 2, 3, that's interesting. 76 plus 123 is 199, and 123 and 199 is 322. So comparing them one for one, it looks like even though 2 is not much miraculously bigger than 0, starting with a 2 versus a 0 creates way bigger numbers. Like we'll see that, especially when we get to like F44 and L44. Those things differ by hundreds of millions, with the Lucas being way bigger by hundreds of millions. So you're thinking these numbers grow fast, like really fast. I mean, it doesn't look like they're growing fast, but I guarantee you, L44 is close to somewhere in the hundreds of millions of the value. And that's only just another, well, 44, another 32 numbers after this one. So in any case, this sequence here below is studied by Edward Lucas, and it's kind of quirky. Here, every fifth number is divisible by 5. And so far, there's no numbers divisible by 5. How far out do you think we'll have to get before a number is divisible by 5? Just throw a guess out there. I mean, we didn't have a lot of numbers out here, but just throw a guess, like 100 numbers? Huh? You guessed none?
I guess not.
Getting weird, but that's right. But none, meaning N-U-N, like the Sisters of the Holy Temple. Shebang.
Whoa. Sheesh.
Okay, no, that's called a homonym. Words that spell different but sound the same, like pickle and pickle. One of them is a thing you eat, the other is a horrendously vomitous bar that a bunch of drunk undergrads go to like grab booty.
But they're still the same. That's it.
I'm glad I'm not on the camera. Okay. Serious teacher here. Wasn't just working. I get it. Okay, so none of them are divisible by 5. That's a fact. None of them are divisible by a bunch of numbers. Actually, one of my research students right now is investigating all of the numbers that don't divide any single Lucas number. So those numbers are quite interesting. What's so 5 hating about this sequence? Well, it's just because we started with a 2 and a 1, you could, if you wanted to think about it very deeply, why just starting with a 2 and a 1 and then having that recurrence relation will force non-divisibility by 5. But that's maybe something for you to think about on the toilet or like wherever you think deep. Do we see any connections between these two lists of numbers? Let's see. I mean, do they overlap anywhere? That's actually a good question. You know, I mean, none of those 13 numbers above in Fibonacci are equal to any of these numbers. So you might ask yourself, is a Fibonacci number ever equal to a Lucas number? And there's a journal that started in 1963 called the Fibonacci Quarterly. And the Fibonacci Quarterly is a journal that for professional research mathematicians to study this sequence, but not just the sequence, the Lucas sequence and their interconnections and also sequences related to Fibonacci and Lucas. And every year or so since then, there's been hundreds of papers every single year. Did I tell this class that I'm proud to say I got rejected from this famous journal?
Yes, and then you also told us that you didn't.
And then I didn't, because of dear Jurgen, oh my gosh, who is still on this earth.
Yay!
Yes, and alive. I don't know for sure, but yes. So yes. So yes, a very famous journal. You should like Google it because all the papers are available before the year 2016. Then they want to start charging you. But yes. So let's add two numbers that are 2 apart, like F4 and F6. That's 3 plus 8. So if we did F4 and we did F6, F4 and we did F6, we get the number 3 plus 8. We get 11. Yay! Is 11 a Lucas number?
Yes.
Yes, it's right there. It is L5. So let's shift over one to F5 and F7. So F5 plus F7, that is 5 plus 13. So we get the number 18. Is that a Lucas number?
Yes.
Which one? L6. So we kind of have this interesting, somewhat eerie connection. We have the subscripts 5 and 7 here. And the subscript for L is the number right in the middle. Same thing with the 4 and the 6. We have those two subscripts. And they conspire together. In between the 4 and the 6 is the 5. So it seems like this might be a true statement in general. Let's turn the page and write a general statement for numbers that are 2 apart. So what we are observing, we said when we added the 3 and the 8, we got 11. So F4 plus F6 equals L5, the number down below, 11. So the sum equals 11. Let's do another one, just like over here. Wow, wow. How about F7 plus F9? That sum is 13 plus 34, which is 47. Ooh. This is provoking in a good way, you know, or provocative. It's neat. We can make a general statement. And this is what your quest is in some of the homeworks due Thursday. If I have Ln, it seems to be the sum of a number to the left of it and a number to the right of it above in the Fibonacci row. So that would be, if this is, if I called 5n, what would F4 be? That would be Fn minus 1. And if I called 5n, what is this 6? That's 1 greater than n. So this would be Fn minus 1 plus Fn plus 1 is equal to Ln. Very important that you be able to understand, to do this, make this abstraction. To go from something like F3 plus F4, F4. Wait, I have a typo up here. That should be F4. What's going on? Some people just tell me when there's typos. Jeez, tease them. So F4 plus F6 equals L5. So what we have to do is make that connection. So I have to, this is video. I want to make sure it's pretty. Like a flower that's not dead and hasn't been dumped on by dog poop. Purdy, you know what I mean? Purdy flower. Okay, so I want you to be able to take something abstract like this 4, 6, and 5 and say, how do I express this in n lingo? You know? Just pretend that number is n. Is this the only possible way to express this? No, there's other ways to express this. We could have said Fn, and then I'm going to skip the next one. So I have Fn, not n plus 1, but n plus 2. Those numbers are 2 apart. And then the number in between, the subscript in between n and n plus 2 is obviously n plus 1. So this is equal to Ln plus 1. So this is an alternate correct conjecture. Does anyone know what the word conjecture means? Math word? Say yes. Does it mean?
It's like something.
Drawing a conclusion? Yes. Is it correct or false? Does it have to be correct? Can I have a conjecture that's wrong? Like, I conjecture that 7 plus 3 is 9. Is that a conjecture? That is a conjecture, especially if I believe it. But a lot of people believe stuff that's wrong. You know, like some people believe in God. Just kidding. But some people like believe in stuff. You know, like that is you know. Some people believe this, a conjecture in mathematics is like an idea that's beyond me. So what I do with my research students, we look at stuff that's unknown, and then we look at this data and we come up with these patterns and we say, maybe Fn minus 1 plus Fn plus 1 equals Ln. I'm basing that on 2 examples. But is this true for infinitely many examples? Is F of 999 plus F 1001 equal to L 1000? I mean, I have to, first of all, those numbers are too big to even consider. But if this thing is true, you have to prove it. And that is what we do in research mathematics. We prove this. And if anyone is interested to know how to prove this thing in the box, come to my office and we can prove it together. And I'll show you how it's done. But right now, you just have to take it on faith that it's damn well true. And damn it, it is. Okay. Okay, let's add a Fibonacci and Lucas number that are in the same column. So meaning they have the same subscript, basically. So we add so F4 and L4, we get 10. So we have F4 plus L4 equals 10. Now we won't see a 10 in the bottom row. Why? Because 5 doesn't divide any single Lucas number forever and ever and ever. So our only candidate is up here, and there's no 10s. But that's okay. We're like building data. We're gonna conjecture something else then. Like, I mean, you know, how about F5 plus L5? We get 5 plus 11, which is 16. Then we scan the bottom row. The bottom row seems like, well, it doesn't have. That's the interesting where the even numbers are placed in both of them. Have you noticed the even numbers are in the same columns? Does anyone notice that? The even, zero's even, by the way. The next even ones are 2 and 4. The next even ones are 8 and 18. Next even ones are 34 and 76. Next even one is 144 and 322. That like weird? Maybe not. The very first number at the bottom is even. The next number is odd. So wait, this might work. Actually, this is a useful word. Okay, so I don't even know if this is gonna appear like in that little screen. We have an even number, and then to it we add an odd number. What do we get? An even and odd is odd. So we start with an even number. We have an odd number. I add the. Actually, you know what? I'll write this on the paper. I think it will be handy. We have an even number there, and then we have an odd number. So then we add an even to an odd, we get what? When you add an even number to an odd number, you get an odd number. And then when I add the next two previous numbers, an odd number plus an odd number is even number. And then an odd plus an even is a odd. And then an even plus an odd is a odd. And then odd plus odd is even, and we see the pattern going even, odd, odd, even, odd, odd, even, odd, odd. So that's like really predictable. So one can say every third Fibonacci number and every third Lucas number is even, and everything else is odd. Okay, so back to the question. 16, ain't no 16 down the bottom row, ain't no 16 on the top row, which means we need to do more work before we can have a conjecture. Unless you have a conjecture already based on the number 10 and 16. And I trust you might. Say, Roger, do you have a conjecture?
I don't know.
Did say in any way possible.
I just thought maybe it would be like Fn plus Ln equals 2Fn plus 1.
2F. Oh. Okay. Roger's being like slickety slick. And he's even giving the correct closed form already. He's saying that Fn plus Ln, and then if we add those things to column, it is double Fn plus 1. So Roger has a superpower, or Roger is secretly doing research in the Fibonacci and Lucas sequences. Before we verify that, let's take a look at one more column. 8 plus 18. What's 8 plus 18? That is 26. So what Roger noted is that this number 10 is twice the Fibonacci number that's 1 to the right of this Fibonacci number, 1 to the right of 3. So 10 is double this 5. 16 is double this 8. 26 is double this 13. Roger's on something. Onto something. Sorry, on something means drugs. But Roger is on to something. Or both. Yeah, why not? It's inclusive. The class. Okay. You go, Roger. You do you. All right, so let's just write this one in black that I just did. F6 plus L6 equals 26. So let's think. This red thing 10 is double F5. This blue thing 16 is double F6, and this black thing 26 is double F7. So we can look here to find a general formula. We can say the subscripts on the F and the L on the left, that number I have to raise it 1 on the right side. So if I have Fn and Ln added together, I'm going to get double, and then I raise the subscript by just one single number, n plus 1 instead of n. If this makes your head hurt a little bit to abstract, then stop doing that. because you'll learn to love this stuff. It helps if you put hearts around it. Okay, so that's a cool fact. adding things like that, we get a double FN plus one. So let's think about more of the intimacy of the two sequences, and it definitely is intimate. These sequences are in love with each other so much. True love, they will never break. Never say never. Let's add two Luca numbers that are two apart. So we added two Fibonacci numbers that are two apart, and they were directly the number in the bottom. So maybe if I add two Luca numbers, maybe they're, well, let's see. Let's add L3 and L5. L3 and L5, which color am I doing? I want to do red. L3 and L5, wow. Do they equal 3? Well, hell no. 4 is already bigger than 3. 4 plus 11 is 15, and 15 ain't 3. But who cares? Let's move on. Let's get some more data. So that's what L3 plus L5 is. Let's get other data. How about we have the number of 7 plus 18 is 25. And that's what L4 plus L6 is. And 25 is definitely not 5. Let's jump to let's just jump to here. So we're gonna add L6 plus L8. So we get 18 plus 47. Help. 65. Okay, so someone want to put on their Roger cap? You got a Roger cap?
No, but.
I mean, not literally the hat. It's a metaphor. It's a metaphor, you know, like.
No, it wouldn't go with my outfit.
Okay. Okay, you got a conjecture for a general force? Like, wait, something about these numbers, 15, 25, 65. Are they related at all to the numbers they're pointing at?
Yeah.
Yeah, we say it at the same time.
No, it's okay, go ahead.
No,
No.
GZ?
I didn't say anything.
Okay, that's you.
Well, I don't know how to say it, like, how to say this eloquently to say Raj did, but
Okay.
what I'm noticing is.
Raj is a high bar, he's freaking insane.
That's what I'm saying.
Okay, sure. Okay.
So I'm noticing that Ln plus Ln whatever, or so, well, I'll just, L3 plus L5 is 15, then F4 is 3, which is, or 3 times 5 is 15.
15. Is that what you're gonna say, Ariella? Yes, 3 times 5 is 15. 5 times 5 is 25. 13 times 5, people say, is 65. So it seems to reason that if we have numbers that are two apart, so I'm gonna do some formula like this, but instead of the F's I'm gonna put the L's. Ln minus 1 plus Ln plus 1. So we have two Luca numbers that are two apart. So we have Ln minus 1 and we add Ln plus 1. Hawk says that we get 5 times what? F something, right?
5.
Okay, group work. 5FN. We get the subscript that is in the subscript n that's in between these two subscripts n minus 1 and n plus 1. In between n minus 1 and n plus 1 is n. So this is unusual, mostly because the Lucas sequence seriously hates the number 5 to the point where it never has anything divisible with. But if we look at the hundreds and hundreds and hundreds, literally, I'm not lying, of identities, this is called an identity, between Luca and Fibonacci, majority of them have a 5 in there somewhere. So for a 5-gating sequence, when it interacts with the Fibonacci sequence, 5s appear like rampantly all over the place. So when I say hundreds of identities, there's a book by Cauchy, Thomas Cauchy, is famous researcher in this world, and it's maybe about 700-800 pages, and it's full of this stuff. And I make sure my students know all of that before they begin research with me. Yes?
What is the significance of this? Like what we're learning right now?
We're just learning about the beauty of the sequence. What's the significance of the Mona Lisa? Same answer.
Oh, it's
We're doing-
useless.
It's useless, but it's actually useful in nature. Fibonacci sequence is all over the place. And it's also used in in stock market analysis, Fibonacci sequence. I mean, it's got some practical applications, none of which I have any desire to ever inspect because that sounds horribly vomitous. Because the series is too beautiful on its own to have utility that's beyond beauty. Yes,
So you talked about all this in your talk, so did you prove all of these, like,
these
principles?
things are well known. But
Okay.
yes, I just make sure that my students can do this before they begin working on new stuff.
Cool.
Yes. Yes. But I think this is just when I look at this, I just say, damn, that's beautiful. Okay, let's multiply two Fibonacci numbers and Lucas numbers that are in the same column. When we added them, they sum to the next Fibonacci number, but times 2. So maybe when we multiply them, something beautiful too happens. So let's start over here. 2 times 4 is 6. There is no 6 below or above. But then we might think, well, over here, when we added them, it was double. Maybe it's double that 3. Maybe it is, you know, like maybe that's what we're talking about. What about 3 times 7? That's 10. No, sorry. 3 times, wait. 2 times, wait, this is 8. Okay, sorry, I'm making, I was adding and, you know, multiplication technically is repeated addition, you know, okay.
You're on the right track.
Yes, I just sometimes need a hug, you know, sometimes I'm just a really evil creature. Okay. Okay, now this is a whole different story. We do see a damn 8. Yes, you have a question, Oj. Oj. Hmm?
Question. I spelled pattern. I think.
Alrighty, can I write some examples first and then you can bust out a rhyme, bust a rhyme? Alright, okay, so hold on to your hat, Olivia. So what about 3 times 7? This is 21. What about 5 times 11? This is 55. They're clearly Fibonacci numbers, and Olivia clearly has something to tell us. What do you want to tell us? Oh,
That was as far as I figured it out.
I thought you had some grandiose thing. Okay. Okay, you have a grandiose thing thing?
FN times LN.
Wait, pause, I need to write. It sounds right as so far. FN, oh wait. FN times,
Equals FN times 2.
the n times 2 is in the subscript? Can we say 2 times n instead, f2n? Okay, so lyric conjectures that if we take the 2 and the 4, this is going to be, f3 times l3 is going to be this, f6. And f4 times l4, remember the word 4, is going to be equal to f8. And f5 times l5 is going to be equal to f10. So yes, what Lyric is noticing is that the subscripts here, when I multiply fn and ln, it's equal to a Fibonacci number. What is the subscript? The subscript 10 is double the subscript 5. Here the subscript 8 is double the subscript 4. Here the subscript 6 is double the subscript 3. So this is pretty dope. This is also very beautiful. Why this is beautiful is that there's other sequences that are different than Fibonacci and Lucas, but they exhibit the same thing. And I'm getting ahead of myself. But some of my newest research is looking at this thing called a balancing sequence and a Lucas balancing sequence, and they multiply together to get a balancing number that is similar to this but different. And that sequence is completely unrelated to Fibonacci and Lucas, but there's a lot of, what do you call that, cross-contamination or between different aspects of mathematics, especially when we're dealing with sequences. Okay, let's do 2 more and then call it and then start doing some new stuff. Okay, let's take the difference of 2 Fibonacci numbers that are 4 apart, like f7 here, and then we go 4 down the road to f3. So we're skipping 3 numbers in the middle. So we would think that maybe this is related to the number that's directly in between them, but is it? So we're taking 13, F7, we're subtracting F3, and we get the number 11. 13 minus 2 is 11. So we do get the thing in the deck set, but that was only one example, so we shouldn't go to town and take it to the bank yet. We should do another one. Let's do these ones. Do F10 minus F6. So those are numbers that we skipped the three numbers in the middle from F6, then we skipped 13, 21, 34, went to 55. So if we subtract 8 from 55, we get 47 miraculously. Ooh. So we get a Lucas number when we take a difference of Fibonacci numbers that are 4 apart. So I'm gonna write the right side, and then one of you tell me what the left side is. So we have an ln here. It's gonna be the sum of 2 Fibonacci numbers. What are the subscripts of those 2 Fibonacci numbers? It's important to build the skill for your homework. Think about this being L8. Think about the number 8 being your n, and then what are the numbers there? 10 and 6. So what's one way I can write these subscripts? F sub blank and F sub blank. What is the first subscript? Yeah, Ryan? N plus 2. Yeah, Ryan is just sound like I called you Ryan for a second. My bad. Well, you can kick my butt after class, but right now we're teaching. Okay, but I'll pencil you in for my ass kicking. Okay, cool. Okay, or butt kicking. Sorry, this is on a video. So what Ryan probably did is saw the 8 there and said, I gotta increase that 2. So if I call that n, I have to increase that 2 to get the 10. That's what the n plus 2 is. Then Ryan said that 6 is 2 below 8, and that's why Ryan said n minus 2. Rocket science. Pretty dope. All right. Cool. So now we have a new one where they just give it to us and they say, what's this equal to? So let's conjecture a formula for fn plus 1 times ln plus 1 minus fn times ln. Let's do an example that is small. How about, well, look at these 2 columns. So we're going to say, we're going to multiply the 8 and the 18. So we get 144. And then we're going to multiply the 5 and the 11. So we get 55. And then we're going to subtract them. So let's be a little bit more formal. We're going to have F6 times L6. So F6 times L6 minus F5 times L5. And what we get is 8 times 18 minus 5 times 55 times 11. Sorry, I'm just doing that multiplication in my head already. So we have 144 minus 55. Notice those are 2 Fibonacci numbers. 144 minus 55 is necessarily equal to the number in between them, because 55 plus 89 is 144. So 144 minus 55 better be equal to 89. So this is 89, which is F sub 11. Okay, that's one example. Let's do another example with numbers that are not so big, I hope. I don't want to multiply 13 and 29, although I could if I wanted to, just don't want to show off. Let's do these 2 columns, like F5, L5 minus F4, L4. So F5 times L5 is still 5 times 11. Now this column we haven't done, F4 times L4 is 3 times 7. So we have 55 minus 21. So we get 34, which happens to be F9. Yeah.
I didn't realize this. So if you showed like F6 and you added F5, you get F11. And if you take
If you take the subscript 6 and add the subscript 5, you get the subscript 11. That's what you mean. Because when we add F6 and F5, literally you get F7, which is F6 plus.
yeah.
But I know what you mean.
You add
Okay.
the subscripts, you get here.
Hope is saying yes. Add the damn subscripts to get the damn answer. Okay. No need to say damn. This is a classroom setting and a temple. Okay. All right. We'll just have to delete that part of the video because of its sheer profanity. Okay. Fn plus one times Ln plus one minus Fn times Ln, Hope, wanna take it away again? Is an F number that is what? What's the subscript then? You said something right. You said that's a 6, that's a 5, and that's why that's an 11. But now we're being generic, we're being abstract. What is this one now? What is the subscript on this F?
You still want a 6 and L.
No, there's no numbers anymore. This was the world of numbers, now we're doing abstraction. What is this abstractly, what is the subscript? Given that the subscripts here are n plus one and these, and the ones on the right are n.
N plus one plus N plus one minus N.
No minus, we simply added the 6 and 5, right? That's all we did, right? That's all we did, just add the 6 and the 5.
N plus one.
Yes, that's it. We're adding those two numbers, n plus one plus n. Now that is fantastic, Yogi. This is the way to say it, but why, we should just say 2n plus one, right? That's what we normally would like do. I mean, not to say that you don't have to be pretty. Actually, in mathematics, there's no room for ugliness. Because it could be so beautiful. Okay, so I'm quoting a very snobby number theorist. He's famous, but I think it'd be better to write this number as 2n plus one.
And that doesn't change like the N now.
No, not at all. It's just like we're just collecting the ends, you know, just collecting the ends.
But isn't that become just 2n plus 10?
2n plus n, that's a different number.
Oh, yeah.
Yeah, that would be 3n's. Yes, cheesy?
If I don't make it free.
No, okay, sorry. In the multiple choice in the web work, there is one and only one answer. If you don't see your answer, that means that you must work with your subscript to make it look like one of those answers.
So I have
Yes.
to see that.
Okay. So enough of that. You are going to be asked about questions like this, but you're also going to be given new things like f5 squared plus L5 squared. And it's going to ask you to make a conjecture of what that is. Ryan, that's a great place.
That's mid-con.
Okay, let's talk about something that's not called Binet. Remember, there's a lot of French people involved here. This is the beautiful Binet formula. So, no, that's got a T and all that stuff in there. Hi, Reed. Say hello. Okay, so who is this fella? I am Jacques Philippe Marie Binet. I was born in 1786 and died in 1856. The Binet formula is named after me in 1843, but it was known over 100 years earlier by Abraham de Moivre in 1718. But why do we attribute it to Binet? Maybe because his name is easier to say than de Moivre. But I love saying de Moivre. De Moivre.
You know French, Alba?
Do I know French? De Moivre. Yes, that means yes in French. De Moivre. Okay. Oh, I wanted to box all my answers. Sorry, my bad. Can you just box this little thing? Because all the other ones were boxed. I just don't want to. And so beautiful. Maybe some hearts. Okay, let's go back to this Binet formula. So one I'm going to ask, what is the 100 Fibonacci number? Well, it's just too big for even Desmos. So let's change this to say what is the 43rd? What is the 43rd? Oh, Reed, can you what? Make a note, no, about changing that from 100? Okay. Thank you. You know, you're so awesome. Did I tell you that today twice? You're so awesome, you're so awesome. Okay, 42nd and 41st. Can we figure out the 43rd Fibonacci number without knowing the previous two Fibonacci numbers? Well, yes, we can. We have a simple closed formula. Remember how the difference equations in earlier part of chapter 11 were solved by star or star star? And we came up with some formulas. This one cannot be solved by star or star star. I mean, we can tell by just looking at this closed form. You should marvel immediately at this following fact. Fn is an integer. Always. But when we look at this, the square root of 5 is an irrational number, meaning it cannot be displayed as a decimal that repeats. So it is got infinitely many decimal representations, and then I'm adding 1 into it, dividing by 2, and then I'm raising it to some freakish powers. And then I'm dividing it all by the square root of 5. And then when you look at this, you should say, there's no way in hell this is ever an integer. But it turns out it is. Yes? Question?
You have the definition of integer.
-3, -4, -5, 0, 1, 2, 3, all those numbers.
Numbers that exist.
Yes, some people call them the whole numbers. I like to not use that term because it's ambiguous.
0.5 would be it.
No. That'd be a rational number. So, great question. So let's get the 43rd one, but I wanted to use Desmos because I can, and we're sharing a screen anyways, so let's go here, go click on Desmos. Where are you, Desmos? Here, Abba. Oh, hi there, Desmos. Hi, Abba. Okay, so let's put in the STAMI. I wish I can copy and paste this picture into here. In the future, we'll be able to do that. Square root of 5. And then I'm gonna have 2 sets, oh, whoops. 2 sets of that. Maybe I should put a times here. And then I'm gonna have 2 sets of that again. And then I'm gonna have a fraction 1 plus square root of 5 divided by 2. And let's just copy and paste this minus that. And then I'm gonna raise this exponent up to positive 43, because we want to find the 43rd Fibonacci number. So I'm going to set f to be the n to be 43. So I'm going to just put an n there, 43, and an n there, 43. So if we do that, we have a 43 here, and then put it over here also, exponent 43. What? Oh, I have, okay, you know why I got a 0? No, because I wrote it in wrong. Both of these things are identical. If I subtract the same thing from itself, obviously we get 0. Okay, so this is supposed to be a minus. Okay, so this number is big. Question? Yes, go on.
Is f0 considered the first Fibonacci number?
Yes. Everything in every sequence we looked at, why not, was always the first one. So like,
That one before the third, the f of 42.
oh, geez, yeah, geez, I guess I could change it to 42 right now. Okay. The 43rd Fibonacci number, that's very, very correct. The 43rd Fibonacci number. Man, you got me saying wrong stuff on video now. Thank you. My fault. I like being corrected. The 43rd Fibonacci number is F42. Okay. Okay, so F42, I can change this 3 to a 2. Oh, actually, this is great. The number will be more manageable, probably less to write. Okay, so we put a 2 here. That was great. I'm glad you said that, Sam. You get a pony. Okay, 267,914,296. Okay, so we have a BAN, big number. Now let's look at the Lucas sequence, and let's consider the 43rd Lucas number. Can we compute it without doing the 41st and the 42nd? Well, yes, we can, because we have this formula that's very similar to here, except that this minus over here is now a plus down here. So we can say L42 equals, and we'll shoot off to Desmos land again, because we can just copy and paste most of that code and change a plus to a minus. So change a plus to a minus. And so we have, so I change a minus to a plus. So we have 599 million. What's that? 599,074,578. But wait, before you, one thing to note, Lucas sequence started with a 2. That was the only difference. And look how vastly larger the 43rd Luca number is than the 43rd Fibonacci number. So when you start with a small number, it kicks butt. So that's it. We'll have more lessons on this later, and I'll turn this camera so you can say hi to all you beautiful people. There we go. Yay. Hey, stop sharing, stop sharing. Man, I don't know how this sticks. This doesn't stick.
You have to, yeah.
After what?
It has to like be, it's like not thick enough.
It's not thick enough. Oh.
We
We had it on this earlier.
Oh, I had it on that earlier. Okay.
Yeah, that's why.
Okay.
There you
Goodbye, everybody. All right, I want to say goodbye to the town too. Bye, everybody. Goodbye. Goodbye. You're immortalized. You're immortalized forever. You'll be famous now.
Every other class from now on, see this video.
Yes, this video will last for thousands of years. Every math 104
Have
student.
you heard that university
You're gonna be.
that like had recordings of a whole professor and he died, but they still use it for.
Oh, that's fine.
What if that happens to you?
Yeah, that'd be fine. I wouldn't mind that.
But the thing is like, is his family still getting paid?
Photo shoots.
That's the question with
Bye,
like,
Bye-bye.
like, you can record like actors, and then you can use like their likeness. Face smaller.
Yeah.
The actors still get paid?
They should.
Do they get a flat fee when they put their headshot in?
I literally just smacked
They
it.
assume the data of their face and they're put on the.
I got no tomatoes, so
They should have always paid for that.
yeah. A load of this.
It's still really. Are you gonna cut this out?
Nope.
I know that I know how to do it. You know what I mean? I'm gonna be honest.
What?
I might fail this section.
Oh, stop. Maybe rewatch the video.
I will.
You know.
I just like every time you guys are like, oh, I figured it out. I'm like, how did you figure that out? We'll see what happens.
Okay, goodbye. I'm gonna stop the recording. Goodbye.